This lesson corresponds to section 12.2 in your textbook, chords and arcs. Define chord. Chord is a segment whose endpoints are on the circle. A chord does not necessarily have to go through the circle, so both of these could be chords. The blue one is a special chord. We know it as the diameter, but chords don't necessarily have to go through the center of the circle. Probably worth jotting down too. Whose endpoints are in the center of a circle doesn't have to go through the center. So it's a line that cuts across the circle. We're going to use information about congruent parts of a circle to find out other information about parts of the circle. So this particular lesson is, I don't know, more weird than it is hard. There's a couple of things that you'll have to notice, and you'll kind of be like, well, that makes sense, which it will, but at the same point, then remembering it and seeing it. So whatever, let's just get started. So in this slide, you don't have to write anything down. It's not on your paper. I just wanted you to see. So if this were class, we would have had a discussion. What is congruent in this diagram and or what can be proven congruent? Well, if you notice these arcs, M, N, and the arc GH are both congruent. Well, what do we know about congruent arcs? Oops, I don't know where my dot went. Congruent arcs have congruent central angles. So we would have said, well, since the arcs are congruent, the angles that made them up have to be congruent. Okay, well that's great. Since those arcs are congruent, what else does that mean? Well, those segments I just drew are the radii. So that means that not only are the arcs congruent to each other because that's where we started, but now the central angles are congruent because arcs are congruent, central angles are congruent. I drew the radii, so that gave me two isosceles triangles, things about side angle side. So we know that if congruent parts of, what was that, CPCTC, corresponding parts of congruent triangles are congruent. So essentially here I have two triangles that are congruent, this triangle here and this triangle here. So if you think about side angle side, I know that this chord length must also be congruent. So it's kind of a domino effect. Arcs give you angles, which give you chords, and it can all be reversible. So if you know the chords are congruent, then the angles were congruent, and the arcs are congruent, so on and so forth. All right, so let me get down to something that's in your notes, because I know that's the reason you're watching, is to write things down. Key concepts. It says in the same circle or congruent circles. There are three key concepts here. Number one is the one that I just discussed. It says two chords are congruent, and the chords are these red lines here. Two chords are congruent, so this would be congruent to that, if and only if the related arcs or central angles are congruent. So if you look in the particular diagram, I have the central angles marked congruent. If those central angles are congruent, then the chords are congruent. It says or if the related arcs. So in the previous diagram, I gave you the 90 degrees here, or any other congruent degree. But if the arcs are congruent, then the chords are congruent. And it's also reversible. If those chords are congruent, then either the arcs or the central angles are congruent. So this here is all reversible. So it can kind of come in either order, which is the idea of if and only if. Number two, it says chords are equidistant. Equidistant just means that they're an equal distance. Forgot my T in there. Chords are an equal distance from the center if and only if they're congruent. So since these chords are congruent, then the distance that it takes you to get from the chord to the center also has to be congruent. And if you think about it too, let me get my eraser, that they're equal distant. Look at those blue lines. Those blue lines are the radius. So yeah, they'd have to be the same distance because whoops, I don't know what happened over there, because the radius are all the same. So they're the equal distant from the center. Lastly, it says the perpendicular bisector of any chord goes through the center of a circle. So if you were to attempt to cut this chord in half at a 90-degree angle, The only way that that could happen is that if it's going through the center. The idea about all of these is that this one's reversible, this one's reversible, this one's reversible. So if you recognize that you have chords that are equidistant, then they're congruent. If they're congruent, then they're equidistant. Same thing with number 3. If they give you the perpendicular bisector, it has to go through the core, or it has to go through the center. If you realize, hey, wait a second, this thing goes through the center, or you draw it yourself through the center, then you've created the perpendicular bisector, meaning that it's 90 degrees and it cuts the chord in half. Let's go ahead and look at some examples. All right, so this is within the table on your notes. It says find the value of x. Not a whole lot of math happening here, but some observations. Notice that the arcs are the same. So the key concept says that if two arcs are the same, then the chords must also be the same. So x is really 11.2. The other thing that is also the same in here, which it's not asking for, but the central angle is both 89. So because we're dealing with the exact same triangle, with the exact same radius, those those chords would have to be congruent. So the key concept used is the one directly above it in your notes. My second one says find the length of x. So the key concept I'm using here is already listed in your notes. Chords are equidistant from the center if and only if they are congruent. So I have two chords. This one is labeled 36. This one is 18 and 18. Those chords are congruent. So that means that they're an equal distance from the center. It shows me that this one is 16 units from the center, so that one is also 16 units from the center. Lastly, number 3, the key concept here, perpendicular bisector of any chord goes through the center. So you can kind of pick it apart and use its pieces. So here's a segment that's going through the center and is perpendicular. If that's the case, then it must be cutting it in half. The x that it gave you is the entire chord, but I could find half of it using Pythagorean theorem. If this is 4 and this is 6.8, I'm going to go ahead and call this y. I don't want to call it x. So I could do 6.8 squared plus 4 squared equals y squared. When I did all the number crunching, I ended up with y equaling the square root of, it's kind of a crazy decimal. Well, if y is half, then this value is y and this value is y. So x is essentially 2 of those y values, which I did end up typing in my calculator because I know you guys like it better, and it gave me approximately 11.0. Okay, so let me explain this one more time. The perpendicular bisector of any chord goes through the center of the circle. So what they pictured, they gave us something that went through the center of the circle, and so it's going through the center, and we were told that it's perpendicular. So kind of using this and all of its reversibility, this would have to be the perpendicular bisector. So x is being cut in half. Once we find half of x, we can add it up to find the whole x. All right, handful. It says you try. So this one, I think the numbers are all goofed up. I think this is number 3 right at the bottom of your notes. It says find the measure of AB. Well, when we talk about measure, we're talking about degree. We're not talking about length. So we're finding the measure of arc AB. I noticed that the two chords are congruent. So since the chords are congruent, the arcs are also congruent. All right, find the value of x. Let's see what we've got here. Well, x, this length is the radius. 22 is the whole chord. And this happens to be a distance, but if you notice, it's going through the center and it's perpendicular. So that means that this part of the chord is 11 and that part of the chord is 11. I think the hardest part of a problem like this for students is they don't see to redraw. A radius can go from the center to any edge of the circle. So essentially what you've created for yourself is a right triangle. this length is 6, this length is 11, and it wants us to find the radius. We redrew it. So 6 squared plus 11 squared equals x squared. I ended up with x equaling the square root of 157, which again, I know you guys like decimals better. There you go. Next problem, find the value of x. Well, x is the length of the whole chord. I know that if chords are the same length, they will be equal distant from the center. Since they're both 9 from the center, that chord has to be 20. Similarly over here, x is asking for the length of the whole chord. It's telling me that they're an equal distant from the other side. This is 3.5. It's not necessarily asking. Notice the center and this thing going through it. This side is 5. This side is 5. So that means x is 10. Number 20. Oh, I'm sorry, number 20. And the next one, 20 is the diameter. So that means this amount is 10. I see a segment going through the center at a 90-degree angle, so this piece must be 8. So I have a 90-degree angle right here, where the hypotenuse is 10, one side is 8, and I'm trying to figure out how far away it is from the center. X squared plus 8 squared equals 10 squared. That gave me, ooh, finally a nice one. X ends up equaling 6. All right, so for sake of a good place to stop, I'm going to go ahead and stop there, and the next handful of problems I'll do in a second video.